To review the accumulation function, I chose a problem from page 180 from the Master Math Mentor document, and this is one of the homework problems or practice problems. So we have the graph of f of x, and the accumulation function is the definite integral from 0 to x of f of t dt. So it's the accumulation of the area from 0 to certain x values. So when we're calculating these, we see that the first one is -4. So that's actually going backwards from 0 to -4. So to help with all of this, I tend to find it easier to kind of fill in what I know already. So let's go ahead and find some areas. So we have a half of a circle here. The circle has a radius of 2, so pi 2 squared. The whole circle would be 4 pi, so half of it would be 2 pi. So each of these little pieces would be pi. We have a little triangle here. That's a 1 by 2 triangle, so 2 times 1 divided by 2. This is going to be a total thing of 1. 1. Here, 2, 2, so it's 4, so we have 2 units. This has a height of 7, height of 2, average of 7 and 2 is 4.5 divided by 2. That'd be 2.25. Wait, that doesn't make sense. Hold on. 2 plus 7 is 9 divided by 2. Already divided by 2. It's 4.5. Oh, goodness. So 7 times 1, 3.5 here. This little part would be a 1. This would be a 3. Okay, so if I was going from -4 to 0, I'd have a 1 minus pi. But we're going backwards. That would make this a positive pi and a -1. So that's pi minus 1. Now, here we're going to have to estimate a little bit, because to get to -3, we've got like a little bit of this, like that'd be like a fourth. So that'd be a pi minus a fourth. To get to -2, that was be a positive pi because we're going backwards. To get to -1, we're going to have to estimate. That's like a, I'm going to estimate a 2/3 of a pi. At 0 to 0, our area is nothing. 0 to 1, I'm going to go with that estimate again. To get to 2, oh good, that's a pi. Oops, I forgot when I'm going this way, both of those would be negative. From 0 to 3, that's a half of a square, so it would be 1/2 minus pi. To get all the way to 4, we'd start that minus pi, but this is a 2. To get all the way to 5, it's 2, 4.5, 6.5 minus pi. Add in 3.5, we're now at 10 minus pi. To 7, we're going to subtract 1 from that. And then we're going to subtract 3 more. Now, the thing about the accumulation function is we have to remember that this is the area under the curve. That is actually our integral, our antiderivative. So if I take the derivative of the accumulation function, I get my original function back. So to fill in these, all I have to do is look at the y values of the graph. These are the y values. So at -4, I'm at 1. -3, I'm at 1/2. At -2 is at 0. At -1, it's like -1.8. 0 is at -2. This would be -1.8. We're approximating what we don't know. At 2, it's at 0. 3 is at 1. 4 is at 2. 5 is at 7. 6 is at 0. 7 is at -2. And 8 is at -4. Now, remember, this is the derivative of capital F. So we're increasing when the graph is above the x-axis and decreasing when it's below. It's just that easy. So F is increasing when F prime is positive, which means when little f is positive. So that would be from -4 to -2, from 2 all the way to 6. Because capital F prime is positive, which also means that little f is positive. It's decreasing on -2 to 2 and 6 to 8. Because that's when f prime is negative and we learn that because that means that's where little f is negative. Minimum and maximum values occur at our critical points. Critical points occur when f, little f, is 0. We also need to look at our endpoints. So I need to look at all of my endpoints and when capital F is 0. Capital F is 0, and capital F prime is 0, sorry. What did I do here? Nobody caught that. When x is 6, I was at 0. Sure. So I need to compare all these y values. I need to figure out which one's the biggest and which one's the smallest. So 6 minus pi is going to be a little less than 3. That looks like my biggest value. F has a maximum of 10 minus pi when x is 6. And if we think about that logically, that's when we've accumulated the most area. Makes sense. F has a minimum of, let's see, which one's the smallest? Positive, 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 positive. It's going to be right there. Of negative pi when x is 2. The concavity of f. So I like to make a number line chart to look at my concavity of f. And that's because we're going to be looking at f double prime, which is little f prime. So from -4 to -2, this graph is going down, it's decreasing, so this would be negative. From -2 to 0, it's also decreasing, it's negative. From 0 to 2, it's increasing. From 2 to 4, it's increasing, but it's still increasing all the way up to 5. And then it starts to go back down. So it's going down to 6, so it's still going down all the way to 8. So F is concave up when little f is increasing. So that would be from 0 to all the way up to 5. And the reason is that would mean that f double prime was positive and little f prime is positive. F is concave down when little f was decreasing. So from -4 to 0 and 5 to 8. And that was because that's f double prime being negative, and we learned that from f little prime. Little f prime being negative. Now on the quiz, I don't ask you to sketch the graph of the function. So we're going to skip that for the sake of time. Now, to review the velocity graph, I chose the back side of the sheet I gave you. It has numbers 6 through 11. And we have the graph of velocity on the interval from 0 to 4. For what values is the particle moving to the right? Well, the particle is moving to the right when velocity is positive. So I just look at the graph and figure out where I'm positive. So from 0 to 1, at 1 we're 0, and then from 1 all the way to 3. The particle is moving left when the velocity is negative. So that would be when we're below the x-axis, so from 3 to 4. And that's when the velocity is less than 0. Forgot to put the because. For what values is the speed increasing? Okay, so speed is increasing when the velocity and acceleration have the same sign. So velocity and acceleration have the same sign on what intervals? Well, here velocity is positive, but acceleration is negative. We're losing speed. Here velocity is positive, and we're increasing, so from 1 to 2. Here our speed is going down again, but we turn around and we start increasing speed in the negative direction. So, from 3 to 4. The speed of the particle would be decreasing if they had opposite signs. So we already discussed that. Here, the speed is 1 and it's going to 0, so that's definitely decreasing speed, also from 2 to 3. The net distance traveled. Notice that's different from the total distance. The net distance would be the area under the curve of velocity from 0 to 4. Taking consideration that we went forward and then backwards. Now this one's kind of a crazy graph, so we're going to have to kind of split it up into figures we know. This figure is a rectangle, but we'd have to subtract a semicircle. So to get that shaded area. So the rectangle will be a 2 by 1 minus half of that circle. The radius of the circle would be a 1, so pi 1 squared would be 1/2. This would be a 1 by 1, so that's a half, and this is a half. So this is a positive half of unit, negative half a unit. Those are going to cancel out. So my net distance traveled is just going to be the 2 minus half a pi. Total distance traveled. That's like the Fitbit. It's going to figure out how far I've gone, and it doesn't care about direction. So it'd be that 2 minus half a pi. It'd be this half and that half. So that's a total of 3 minus half a pi.